In class this week, we talked about inheritance and polymorphism, that is dynamic dispatch or runtime dispatch of function calls. We talked about virtual functions, and we talked about the problems of slicing when putting concrete types into containers. It breaks our polymorphic functionality. Before we go on to use pointers in this case in our demonstration project, I wanted to just do a repetition video showing the same exercise that we did in the classroom to make sure that we're all on the same page when it comes to the syntax and how it works. So this is just an empty an empty Win32 project, and I've activated the console subsystem so that we get our output. We're going to need some includes, so I'll bring in IOStream. For output, I want to include memory for smart pointers, which we'll use at the end. And I probably want the vector in here as well, so that we have a container to put things into. Maybe we won't bother with it. Once we have the pointers, we already know the solutions, right? I'm also going to, for once, make use of namespace standard. This command means that the standard scope, all of the methods available in STD, all of the objects and all the symbols, becomes implicitly, or rather this statement becomes implicit in all lines. So we bring the entire namespace, all the symbols, into this file. It's not elegant, but it's less typing. So, you know, whatever floats your boat. I want a canonical main. So one that takes an int for argument count and a char pointer vector with C-style strings. And then I want two classes. I want a base class and a child class, or a parent class and a child class, or a base class and a derived class, or any of the other words you'd like to use to describe these things. I'll use the same ones. So class animal as the parent class. We might want a constructor so that we can print when it's being created. Animal created, and a new line is probably smart. We need to make that public, otherwise we can't actually create any objects, right? The classes are private by default. We make the constructor public and also give some output. Animal destroyed. And lastly, I want a public function to feed the animal. So a void function, let's call it eat. Just going to copy the output strings. I'll make a tab here to get some white space in the output. I'll try to create a local animal on the stack. That's what local means. That's not okay because it's, what is undefined? Identifier A. Class animal ends here. No, okay, we're good. That's interesting. So we create a variable of type animal, and the name or the symbol is A. When A leaves scope down here, the animal destructor is called. This object goes out of scope. This is on the stack. It's automatic memory. So control F5. Animal created, eating, and then destroyed. Now, if this was a dynamic memory object, if we, instead of creating the animal here on the stack, we create a pointer to an animal somewhere else, this would be a pointer to an animal. We get the pointer by calling new animal, which places the object somewhere on the heap, right, the larger dynamic memory area. And to be able to call a function inside through a pointer, we have to dereference the pointer, and we do that with a dereference operator. So this is dereferencing, calling the method on an object that this pointer points to. But what's notable here is that this object, created on the heap, will survive our main. For every new, you have to make a delete to make sure that this thing dies, otherwise it will live forever. So control F5. We have created it, we're feeding it, but it doesn't die. So for that to be cleaned up, we have to manually call delete A, or delete whatever the name of your pointer is, when we're done with it. Here we go. So created, eated, and destroy. This is not trivial to get right in real code with more complex flow, logic flow through the application. And so to avoid having to deal with this, whenever you see a raw pointer in code, or whenever you see a naked new, you should replace it with one of the shared pointers, either make unique or make shared. And the pointer with shared pointer or unique pointer. They both work similarly, except a shared pointer can be copied around and the unique pointer cannot be copied at all. A unique pointer is the only owner of that object. So to show you how to use them, you would have a unique pointer of type animal. We can call that pointer, or let's call it uPointer for unique pointer, equals make unique and animal, and like so. That's a unique pointer, and then we can speak to it like this. And whenever we leave main, that object will be destroyed automatically. We can test this. There we go. Created, eating, and destroyed. If we wanted a shared pointer, very, very, very similar. You make a shared pointer of type animal. Call it a pointer now. No, S pointer for shared. Make shared animal. No, there we go. And now we can speak to the shared pointer. Same way, dereference, call. It's the same as using a regular pointer. You're dereferencing in the same way, only now the lifetime is scoped to the pointer's existence. So both of these creates objects, feeds them, and then destroy them. So far, so good. Always, if you have a naked pointer, try to make it one of the smart pointers. If you have a naked new, try to use make unique or make shared instead. And if you have to use a raw pointer because maybe the destruction process is complex or different, like say in our SDL code where destruction happens by giving the pointer back to SDL, you wrap that naked pointer in a class. If you ever need a new function call or a delete function call, make sure that they go into constructors and destructors. So that's how we get the benefits of smart pointers, but without using the smart pointers. We wrap pointers in classes. So much for smart pointers. Let's see if we can try the virtual functions of having dynamic dispatch, or polymorphism as we call it. So we do class cat inherits publicly from animal. Do I want constructors? Yes, let's see how the construction works as well. So we make a constructor. I'm going to just copy this, in fact, save us some time. So cat created, cat destroyed. I am eating mice, so we know what that is. And just to be clear, we can actually give some white space here. The constructor, of course, is named after the class and nothing else. Give me a second. Cat, cat, cat. Give me a second. I just need to go and do a thing. Right. So cat constructor, cat destructor, we need to make them public, otherwise it won't work. And if you remember from the lecture, we need to make the function that we want to have polymorphism on, the one we want to have dynamic dispatch on, we want to make it virtual. So in the base class, in the parent class, make the function that you want to make available for overriding, make it virtual. And if you have a virtual function, make sure that the destructor is also virtual. So now, when we create a cat and call eat, sorry, let's do this the way we did it in the class. I'm going to fold these classes up. So we have virtual functions for eat and the destruction of the animal. Bring that up here. I'm going to disable the pointer stuff for now. Just copy that out. So what do I want to do? Let's see. We create a local cat. And let me just make sure that this actually works. We call cat eat. Okay, so one thing to notice that we might not have covered super specifically is that when we call the cat constructor here, it first creates an animal, then it creates the cat parts. Then we can use the objects, and then it's destroyed in the opposite order. Let me see what happens if animal's destructor is not virtual. See if that makes a difference. No, that seems to work here. So whatever the reason for having a virtual destructor, this is not the case. Anyway, so yeah, in the same way that a class first constructs its members' properties and then runs its own constructor, when we create a child class, it first creates its parent and then it creates itself. So first the parent part, the base parts, and then it builds itself on top of that. Now, we don't want our code to deal with specific classes. We want to be able to use entity instead of using paddle or ball or whatever else we use in our games. Particle effects or bullets, right? They're all entities. In this case, cats are animals. A dog would be an animal. Any animal you can think of would be an animal. So a function we make should deal with animals. So we can make a void function, call it feed. Let's take an animal A and call eat. Now, this function takes an animal by copy. There is no reference, no pointers. So if I pass in the cat, let's see what happens. Feed the cat. We create an animal, we create a cat, then we feed an animal. This is the animal output, not the cat output. And then because we created copies when passing the arguments, they get destroyed in weird ways here. You should try this yourself and try to follow the logic, but the takeaway here is that we run into slicing, in that the cat, when passed as a copy into feed, gets sliced. The cat parts are not available inside this method because reasons. That's what slicing does. There is nothing inside this function that allows it to treat an animal concrete type as anything other than an animal. So the cat builds on top of animal, but inside feed, with this argument being a copy, we don't have access to the cat parts. You could do a dynamic cast, a reinterpret cast to force C++ to read this animal as a cat, but that's very, very dangerous and should be avoided. The proper solution is to pass in a reference. By not doing the copying, we get rid of the slicing. So by sending in the address to our cat, the dynamic dispatch keeps working. So now it's an address to an animal, and I run this. And all the output is now cleaned up, right? We're creating a single object, we're feeding a cat, and then a cat is destroyed. And just as the construction happens in the order of first base class, then child, the destruction goes in the reverse, first child, then base class. So by passing in pointers or references, we allow polymorphism to work. If you pass in by copy, you may slice your object hierarchy. So you only get the base class. Base class, no inheritance, or rather no polymorphism, with reference. We have polymorphism. And this works whether you're using references or pointers. So we can pass in a pointer to an animal. And when using a pointer, as you know, we have to dereference to call methods on the object. This is the object somewhere in memory, right? This is a dereference. This is just an address. That A, just an address. So go to the address, dereference it, call eat on the object that you found there. And this will make use of polymorphic dispatch. We don't have a pointer here anymore, so either I can send in the pointer of our local object, that works well, works perfectly, and having a local object is generally a good idea, right? Anything you can have locally, anything you can make on the stack is a good idea because it's automatically cleaned up. And if you can't do that, you can use the shared pointers or the unique pointers. The unique pointer is not going to work because you can't pass that into the function simply. There are ways of doing it, but I don't think it will work like this. Let me try with the shared pointer first, see if it deconstructs. No, because this only takes regular pointers, right? We can't call this function. We need a function for the smart pointer type. So in this case, I want to be able to pass in shared pointer to an animal. So that should work. Let's try that. Animal created. That's interesting. I only get animals. Yes, of course. I'm not creating cats. So let's create a cat instead. But I'm putting it in a pointer to an animal. Because we have dynamic dispatch, it doesn't matter. Animal, and all right, we're making two of them. That's why. That makes sense. So that worked. And if I try to do that with a unique pointer, we should run into problems because the unique pointer cannot be copied. It's only allowed to exist in a single copy. So if we try to pass in the unique pointer, yeah, it doesn't even allow me to try to compile, cannot be copied. I wonder if I can do standard move on that thing. Move is in the standard namespace and allows you to move the unique pointer into wherever you need it to go. So in this case, what I'm saying is this pointer is the only owner of this object, of this cat that we have created. When this unique pointer goes away, this object is guaranteed to be destroyed. The fact that it is the only owner, the only thing that is allowed to point on this object, means it cannot be passed to this function because this would be a copy of that pointer. So you would have this copy and this copy pointing to the same object, and that's not allowed for a unique pointer. By using standard move, I am giving the cat to this pointer. So now the cat will be destroyed here because this pointer will go out of scope and it's the last copy of it. I think that's what will happen anyway. We might set a breakpoint and see. Actually, that would be here, I guess. Here we go. And if I do step into, yep, we went into the destructor. Pretty sweet. Let me see if it actually worked, though. I think it worked because, well, it compiled and run. So Control F5. Yes. So unique pointer is, it seems like it's super limiting and forcing you to work differently than using a shared pointer or a normal pointer, but that's a good thing. Unique pointer explicitly states, I own this object. I am responsible for this lifetime. So when you're making a class to wrap a pointer, and that class should not be copyable, like say our renderer, for instance, in the game code, right? It holds a renderer pointer, and we don't want multiple copies of the renderer. We want a single renderer for our single window in our application, right? If you wanted to make that render pointer more securely implemented, if you wanted your class to be more securely implemented, you would make that render pointer a unique pointer. That way, it's guaranteed to get destroyed with the class automatically without having to do anything with the destructor or disable copying or anything of the manual work you'd have to do otherwise. But yeah, unique pointer is trickier to work around, so you can ignore it for now, right? You will get into it with more advanced C++ courses, and the shared pointer offers the same benefits, only with slightly more overhead and a little less control over when objects are actually destroyed. They will be destroyed, but you don't really know when, because you can have multiple copies of this pointer, you know, keeping the object alive. It's when the last copy of the pointer goes out of scope that the object is destroyed. And again, a normal pointer here would mean we have a memory leak. So new cat, and we can pass that into feed. And we will never lose the cat. It just doesn't die. Created, and eating doesn't go away. Because the pointer goes away, the object lives on in the heap. So yeah, enough of jammering. Polymorphism, virtual functions, can work with the animal pointer and still reach the cat functionality. In game code, as you know, we tend to use this in the entity hierarchy. Our game objects are entities, and then we can call update on entities and render on entities and collision detection on entities, and they can all share a lot of properties, which means we have less redundancy in our code and a more robust code base. So let's continue with the game in the next video.